I was curious as you're going and learning all of these things about all of these non-human animals. I imagine there's a lot of pretty easy parallels to make with say a lot of primates. What's some of the furthest species from humans that you are drawing parallels to humans, that you're learning something about a bird heart or what have you?
Right. So I I love that question because I don't come from the field of, I did not train to be a behavioral ecologist or I come from the human side, and then I kind of made this leap. I kind of had to invent my own way of looking at things. And a lot of my colleagues, so now I have an appointment in human evolutionary biology at Harvard and at UCLA in ecology and evolutionary biology. And most of my colleagues have studied, either one species or one taxa, very often primates, not always, but very often, for the obvious reasons, right? A closer evolutionary relationship. Mm-hmm. But because I didn't have that background, I didn't start with that perspective. And instead, I was curious about how far leftward we could look. And if you're looking at a phylogeny, just turn your head to the left. If it's a horizontal phylogeny, how leftward we could look and still see those physical or physiologic connections. And the very 1.0 version of this was to just say, okay, breast cancer. So, okay, it has to be a mammal. So we'll go back a couple of 100 million years. But I would literally look for other mammals where breast cancer had been reported in the peer-reviewed literature, and then just kind of take a look at all these species and look for a common ancestor. And, not that necessarily proves anything, but just to kind of give myself a sense of, well, when did the vulnerability to these problems emerge? I mean, who was the first mammal with breasts? Circular thing to say. And were they vulnerable to breast cancer? Why is it then that certain mammals seem to have less vulnerability than others? And those kinds of questions really instantly took me out of one narrow taxa and looking in a far broader way. The other piece of that, of course, is the new research that I've been involved with, looking at biodiversity as a source of solutions for complex human pathophysiology. So as a cardiologist, I've been working on a problem that there's a heart failure that happens in older people. It's caused by hypertension, high blood pressure. So if you just talk about the U.S., the demographics, we're getting older. High blood pressure is very common. And when the left ventricle, which is the ventricle that pumps blood to the systemic circulation, like any muscle, when it faces a higher workload, it starts to hypertrophy. It starts to thicken. And as it starts to thicken, it starts to fibrose. There are these changes that happen to its architecture that make it stiff. And what that means is, even though it can contract well during systole, which is that squeezing phase, during that relaxation phase, it's too stiff and the pressure doesn't fall. So the pressure inside the heart, in the left heart, rises and rises and rises into the left atrium, into the pulmonary circulation, and that causes heart failure, shortness of breath. So and by the way, I'm trying to focus my research on issues related to women's health specifically. So it turns out this form of heart failure is now the leading subtype of heart failure in women in the United States. So I thought, well, what animals, so the concept of turning to nature, to kind of thinking of biodiversity as just multitudes of variations in all of these physiologic components. I mean, every single, big, large. What other animals have ventricles that face higher, quote unquote, than normal pressure? It's normal for them. And of course, easily the answer is the giraffe, which, every medical student is taught that the giraffe has a thick ventricle because, she needs to pump blood from the, down here, the heart is between the legs, up to that brain a few meters, up there. And it's true. But there's another interesting reality about giraffe, and that is that they are prey animals. The leading cause of death among, giraffe on the savannah is predation. Mm-hmm. And so imagine the selective pressure on giraffes to not have shortness of breath and exercise intolerance, the precise symptoms that human beings who have thickened ventricles because of high blood pressure have. And in fact, what my lab's been working on, and what I'm very excited about is finding the adaptations, the differences between the okapi heart, for example, and the giraffe heart. The okapi doesn't have a long neck, right? And the modern giraffe and the modern okapi, they shared a common ancestor about 11.5 million years ago. And as the giraffe cervical vertebrate enlarged and that neck got longer and longer for reasons that have to do with improved fitness, and there are several theories about that, this new selective pressure emerged. And as a consequence of this evolution's, iterative over and over, there is this evolved adaptation that is essentially a roadmap for solving this form of heart failure in humans. So I love the idea of reconceiving biodiversity as something that is alive and relevant and so much more than just looking at the beautiful world and experiencing and appreciating it. All that is fantastic. But really recognizing that the treasure that it is also contained at a much more reductive level. So that's a lot of fun.